Hi everybody, Mr. Lee here. In this video, we're going to do a couple of problems that deal with impulse and momentum. Alright, let's begin. So I'm just going to come up with a scenario, and these are the typical kinds of scenarios that you might see in your everyday classroom practice problems. Alright, so the first one will be, let's say we have a ball, and this ball is falling towards the floor. Okay, and after the ball hits the floor, the ball will rebound back up. I'm going to move the ball over a little bit, but it's going to rebound back up. Okay, so within this problem, the problem could ask, what is the impulse on the ball, or what is the force that is on the ball, or how much time does it take for the ball to bounce or to rebound? So we're going to take a look at all of that in just a moment, and then we'll deal with the numerical part. Okay, so we know that impulse is the force that acts on the system on a period of time. And when a force acts on a system, we know that the momentum for the system will change. Okay, and so I like to always start off with the equation as a whole, and then I like to break it down into its variable form, but a little bit more expanded. Notice here, I'm not putting down the J for the impulse, and that's just because every single part of this equation is basically describing impulse, right? Force times time is impulse. The change in momentum is the impulse. So everything here is describing the impulse. Okay, so now that this is set up, all we have to do really is to just rearrange the variables based on what the problem is asking. And so I just wanted to give you some pointers and some highlights on exactly what to do when you're given a situation like this when a ball drops to the floor. Right? So let's say, we'll just make things simple. We'll say that the ball has a mass of 1 kilogram. Okay? And right before it hits the floor, we can say that the ball had a velocity of, now watch what I do, it won't always tell you this. The problem sometimes might just tell you the speed, but let's say we will say that this is negative 10 meters per second. And the reason why I'm saying it's negative 10 is because direction is important. Okay, direction is important. Now sometimes a problem might just say that it's moving downwards, and it's up to you to make that connection that anything that's moving downwards we can say is negative. Alright, so it hits the floor and it bounces back up, and let's say when it leaves the floor it has a velocity of, at this moment, as soon as it leaves the floor, let's say it's, we'll do exactly half, 5 meters per second. Okay, so as soon as it's about to hit the floor, the velocity is negative 10 meters per second, and as soon as it leaves the floor, the ball is said to have a velocity of 5 meters per second. And once again, here, the direction is positive, and that's because the ball is moving up. And remember, direction is important here. Okay, the ball is moving up. Okay, so let's go to our equations, and let's just do a quick checklist, right? Let's see if we could just add a little bit more to this problem. We're given the mass, very good. We're given the final velocity, good. We're given the initial velocity, which is good. So right here within this problem itself, we can figure out what the change in momentum is. Let's say we can say something like, I don't know, if the floor exerts a force of, let's say 100 newtons. I'm just making the numbers up here, right? So if the problem says the floor is exerting a force of 100 newtons, we now have the force variable checked off, and so now we can actually find the missing variable, and I'm going to do a blue pen here, put a little X there because that's the only one that's missing. So now we can figure out the time it took for this ball to have that impulse. Now, I just want to point out here conceptually what that means. So this delta t here is the time the ball felt the force from the floor. Okay, and so if we were to do like a slow motion kind of imaging of this, and there are tons of really cool slow motion videos out there of like a rubber ball hitting like a bat, or a rubber ball hitting like a golf ball hitting a club. But what happens is I'm going to do a a profile, right? So I'm gonna say that this is the floor. And so we have the ball, and the ball is coming in, and then as soon as it hits it, I'm going to do like a frame by frame kind of thing, right? So the ball hits it, and then as soon as the ball hits it, it kind of like deforms a little bit, like so, right? So this is like time passing by, and it kind of like ripples, like so. Yeah, it's really cool to see, right? It kind of like smushes in, and then I'm gonna do one more smush, right? A really flat smush. Okay, and then it goes backwards in time. And so if this is the ball initially hitting the surface, so the time will start here, this will be t initial, and then this will be like t1, this will be t2, this will be t3, and then it'll start to go backwards in its deformity, right? This is like t4, and then from there we did something like this. This is like t5, and then up until right here where the ball reforms itself like that. This is T6, right? So during this entire process, the ball is feeling a force. So here there's a force, right up until it leaves the wall, there's a force being exerted. And so during this time, now it's hard for us to see it with our naked eyes because, you know, we can't see that in that short amount of time frame, but this is actually what happens, and we know this because we have the slow motion technology to see this in action. It's really, really cool. And so here, when it's talking about delta t, it's talking about the time the ball felt the force from the floor. So during that time, we can say, according to what I just drew, that would be from t6 minus t0, right? That will be your delta time. That will be the total elapsed time that the ball felt the force from the floor. All right. So that is one type of problem that you might see here. Another one is, let's say we just have, I think that's the most complicated one, where the ball changes directions. You might see another one where it's like a ball, and let's say there's a baseball bat, right? So there's a ball and a baseball bat. Okay, and the ball is heading towards the bat, and the ball strikes the bat, and then the ball, because it's being hit, it goes in the opposite direction, right? So here it's important to note that the direction is important, okay? And the direction is definitely important in terms of the velocity, because the change in velocity from a positive velocity to a negative velocity, because the direction itself is changing, whenever the direction of a object changes like that, the force is always greater, okay? Because you're basically, you know, stopping the motion of a ball. You're going against the laws of inertia, right? An object in motion stays in motion, and so you're trying to change that direction as a whole. So that's something to keep in mind, and this will pop up later on when we talk about different kinds of collisions, and the questions are always like, you know, between collision A versus collision B, right? Whatever the collisions might be, which collision exerted the greater amount of force, which collision had the greater force, right? So I'll give you a scenario here because I'm talking about it. And let's see. So we have a ball. Let's do a different one. Let's do the ball actually. Okay, so we have collision A. So the collision A is when the ball is moving forward, it hits a bat, and the ball moves in the opposite direction. Okay, so this is, we'll call this collision A. Okay, and in collision B, the ball is moving forward, it hits the bat, but it doesn't necessarily bounce back because the ball is like, we can say the ball was moving so fast, and the ball and the bat didn't like, you know, do much to it, and so the ball keeps on moving forward, right, after the bat hits it. So this is collision B. So in collision A, we can say that there's a rebound, okay, and in B, it just moves, it continues to move forward, okay? And so if the question were to ever ask you, in which instance was the impulse the greatest, right? So impulse greatest. So in which case was the impulse greatest? That's also asking in which case was the force the greatest, force the greatest? It is always, 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 and this is one of those star kind of moments here. So I'll get my galaxy pen, right? This is a star kind of moment. The force is always greatest when there is a rebound. Okay, F is always going to be greater, right? So always remember that, and mathematically, it always comes true. All right, cool. So that's it for a how to do these impulse type of problems. It's very straightforward, and the only thing we really need to keep in mind, as we discussed in the very, very beginning, is keep in mind that the direction does matter a lot. So anything that's moving down or to the left, you should always write down as negative. Another thing to keep in mind is that the change, that triangle change is always final minus initial. And that minus sign, it might come useful for when you are doing your problems. All right, next time I'm going to do different kinds of collisions, and I will see you then. Bye-bye.